Good morning, good afternoon, good day, good evening, wherever you are in the world, and welcome to Haystack Live. This is our regular meetup on search and relevance. And thank you all for coming today. Today we have a fantastic talk on Milvus, which is described as the world's most popular vector database. But popularity isn't everything, so we're hoping to hear about its amazing technical features as well. So thank you in advance to our presenters today. A couple of other things to mention. We are recording this talk and it will be available on the OSC's YouTube channel later. So in case you don't know, I'm Charlie Hull from Open Source Connections and we host the Haystack conference. I'll be talking a bit at the end of the event about our forthcoming Haystack conference. Yes, a real in-person physical conference. We're going to take the risk and try and plan one and hope it works. Also, you'll see on the screen here, we have a link to our training sessions, and we're just about to publish new dates for our training Think Like a Relevant Engineer courses in late September, and there'll be a Learning to Rank course in early October, and that's bracketing our physical conference. So do check those out. The tickets will be on sale very soon. So the way this talk's going to work, our presenters will be online soon and telling you all about Milvus. If you've got a question for our presenters, you can use the Zoom chat to let us know your question. While our presenters are speaking, if you could mute your microphones, that would be great to prevent any background noise and also helps the quality of the recording. At the end of their talk, I will ask the questions on your behalf and try and make sure everyone gets a chance to ask their questions. I may ask you for clarification if I can't understand the question, which is entirely possible. So that's about it. And we're really looking forward to hearing about Milvus today. This is part of a series we've been doing at Haystack Live on maybe some of the lesser known search engines or search engine solutions. So without further ado, I'm going to welcome our presenters today. Hopefully, guys, you can introduce yourselves and then off you go. So please.
All right, wonderful. Thank you very much for that introduction, Charlie. So, hi everyone, I'm Ryan. I'll be presenting our first presentation today. Just going to give a brief overview and introduction to Milvus, and then my colleague Xiaofan will be giving a more technical presentation right after. Go ahead and share my screen. All right, wonderful. Can everyone see that? Take that as a yes. All right, good morning, everyone. Hope you're all doing well today. I'm here to introduce Milvus, our open source vector database. So let's do some quick introductions. My name is Ryan Chan. I'm a recent graduate of UC Berkeley. Since I've graduated, I've been working in Zilliz as a data engineer, working directly with users to get Milvus up and running in their systems. So what is Zilliz? Zilliz is a technology startup company focused on developing data science software. That's us. We drive our software business model through open source, working to become the standard in vector-based databases. The company started in 2017 and is currently transitioning the headquarters from overseas to the Silicon Valley. Our open source project Milvus joined the LFA AI and Data Foundation as an incubation project in March 2020 and recently became a graduate project of the program. So before we go into Milvus, we have to understand the problem that it is trying to solve, which is what is unstructured data? So data is really divided into three categories, we like to think of it. First is structured data, stuff like strings, numbers, dates, things with defined patterns, easily quantifiable, easily operatable on. Next is semi-structured data. So you can think of this as data that has a certain amount of structure to it, such as like text with a certain format, but there is some randomization or unpredictability to it. Some examples would be like log files, JSON, those sort of things. And the final category, unstructured data itself, really accounts for about 80% of the data that we encounter on a regular basis. Things like images, videos, audios, things that aren't quite easily understood by machines in the format that we find them in. So structured and semi-structured data can be handled pretty easily through traditional parsing, relational databases, but unstructured data really hasn't had too many good analytical methods until recently with the rise of deep learning and everything. So deep learning has given us the ability to transform this unstructured data into something machines can understand in the form of embedding vectors being vector representations of this unstructured data. Now, for some use cases, performing a few operations directly from here may be sufficient for applications. However, for applications looking for better organization, or if we're looking to manage and correlate really large quantities of vectors, there are a lot more challenges involved. Now, this is where Milvus really comes in. So enter Milvus. Milvus is what we like to call a vector database. It shares some basic properties with traditional databases, but it's designed around vectors and efficiency at the 100 million plus vectors scale of data. Probably the most important function of our system is the ability to search for similar vectors. Finding the most similar vectors out of a set, also known as finding the nearest neighbors, is an expensive and slow computation method when using more traditional methods. With Milvus, we can perform an approximate nearest neighbor data search on a massive corpus of data at pretty efficient speeds. So we recently released Milvus 2.0, which was a ground-up redesign with an entirely new architecture designed around scalability. So a bit about our old system, Milvus 1.0. Milvus 1.0 had a pretty rudimentary form of scaling, requiring shared storage and being limited only to have one node for importing data and indexing. This form of scalability was kind of passable for many use cases, but as we've been talking to users over the past few months, past few years, more and more people have been looking for something that is a bit more cloud oriented in their search. So this is where Milvus 2.0 steps in. 2.0, we realized that we needed to make Milvus cloud native. With Milvus 2.0, we bring full elasticity, allowing users to independently scale their data nodes, query nodes, indexing nodes. Another highly requested feature that we've introduced with 2.0 is the addition of scalar filters, which is allowing users to attach filters for fine-tuning search locations and results on their data. So these features and more details about the actual system architecture itself will be discussed by my colleague Xiao Fan after this presentation. So real-world cases. Although Milvus is still a pretty young project, many users are already using it in their production AI applications. A few big examples include Alibaba, Tokopedia, Lucidworks. We believe that the biggest reason that users are choosing Milvus is due to its ease of use, its ease of deployment, and its speed. An easy to use and fast service ultimately results in lower cost overhead for developing solutions and moving to production. We all want that. So our goal is to set the standard and open source software for vector similarity search. Through continuous feedback and improvement, we're striving to make Milvus the best it can be. And with over 1,000 Milvus users and counting, we think we're on the right track. So all this so far has been kind of spoken in general terms. So let's get into some concrete examples of real world use cases that take advantage of Milvus. The first example I'd like to bring up is a smart housing search and recommendation system. Baika, the Chinese equivalent of Zillow, is using Milvus to speed up and expand their housing search software. This is accomplished by first extracting 4 collections of feature vectors from the input information using machine learning models. This input information can be things like floor plans, area, outline, house orientation, you name it, anything to do with the property. Next, using these 4 collections, Milvus performs a similarity search to find the closest results per collection on the inputted house parameters. And finally, the results of the similarity search are congregated, and the closest houses are returned as the recommended properties, sorted by a ranking system. Okay, so another application of Milvus that is very popular with our users is a reverse image search. Lots of use cases for this. Let's take a look at an example that uses Milvus to perform a reverse image search to match a photo with a product listing. In this case, the user used 2 neural nets to pull out an embedding. They first use a tuned YOLO net for object detection. Then they used a ResNet to generate the actual image embedding itself. They put these embeddings in Milvus, and then with these embeddings in the vector database, they could perform a similarity search on images after generating another embedding vector with the same process in order to find the closest matches. All right, let's get into another use case from Tokopedia, which is one of the largest e-commerce services in Indonesia. So Tokopedia needed an updated search engine. They were using Elasticsearch to match raw keywords within product names and descriptions. So this works for finding documents that use the same words repeatedly, but it's a flawed approach. What happens when you have two products that perform similar functions, but have, say, differently phrased descriptions? Just a keyword search correlating these listings is pretty difficult. So the new method is to generate what we call word embedding vectors using the product names and descriptions. The word embeddings replace words with vectors that map to areas of similarity between words. Then these word embeddings can be put into Milvus and similarity search can be formed to find the products that relate. All right, another interesting use case for Milvus is music recommendations. So the first step for encoding a song is to separate the background music and vocals. This is done with techniques such as audio inversion. The next step is to get embeddings built up from background music. Background music is a pretty common choice due to having more information about the song, and you can avoid misclustering due to things like cover versions, having different vocals for the songs, things like that. So with these embeddings stored in Milvus, you can search the current song the user is listening to find similar songs, and deliver them as recommendations to the user. All right, now one final example. Now this is a project that I think is really interesting. It's Milvus, and it involves Milvus in a pharmaceutical molecular analysis application. This is a little different from the rest of the examples, as the core business value really comes from Milvus itself. So this application works by encoding molecular formulas as a 1024-bit binary vectors. With these vectors stored in Milvus, a Tanimoto distance, which is equivalent to a Jacquard distance for binary data, similarity analysis is performed on the queried molecules. The result of this search is a molecule that is close in structure and composition to the queried one. Now, these results are important as researchers are able to discover how a molecule might react to certain medicines based on how similar molecules also react. Now, the end results of this application are pretty impressive. The previously used Spark cluster to perform the same operation was able to search through 30 million molecules within 14 seconds. Our Milvus cluster was able to search through 800 million molecules within 1 second. That's a pretty big speed up. All right. So at the end of 2018, when we were developing a heterogeneous analytical database system, we were exposed to the demands for hundreds of millions of image searches. At that time, the open source community already had a number of nearest neighbor algorithm libraries. A few of the more well-known ones were Face, HNSW, and Annoy. But is it really enough to just have the algorithm library? So there are a few things that we observed when we were looking into this question. First, when analyzing the requirements and designing the system, we found that if we wanted to implement an image search system, we needed to support things like different types of indices according to different application scenarios. One example for this is the difference between a recommendation system and something like a facial security recognition system. A recommendation system, you'll probably want faster speed, while the recognition system for security, you probably want a better recall, and you're okay with making some trade-offs with speed. So another thing we realized that we needed to support multiple database tables, different data collections, and more often than not, data really didn't come in a singular form, and to accurately analyze it, you need to process each form separately. So a system would have to support the creation, reading, updating, and deletion of vector data, all the standard CRUD operations, and even the operation itself has to have certain transactional requirements. Then if you wanted to do any of this in production, it would also need to provide high availability. And with the large data scale, it has to be able to scale linearly, ideally. So we found that all these things that I've talked about are commonalities needed in pretty much every project involving nearest neighbor searches. So unlike the more raw algorithmic libraries, Milvus really offers them all. For this reason, we believe our project is the best choice in the majority of applications where a vector database or vector searching is needed. All right, and that's just about all from me for my introduction. We love to encourage users and prospective users to join our community platform. So you can find our project on GitHub at milvus.io/Milvus. We're open source. We love when people raise issues, as strange as that sounds, or make PRs. So if you're interested in helping out the community. If you want to get in touch with us, you can join us at our Slack on milvusio.slack.com and follow us on Twitter at milvusio for announcements, other content we put out. So thank you everyone for listening, and I'll be handing things over to my colleague Xiaofan for a more technical rundown of Milvus.
I think you're muted. Hello, we can't hear you. You're muted, I'm afraid.
Xiaofan, you're muted.
Okay, so guys, you can see my screen?
Not yet. No, you need to click share screen at the bottom there.
Okay.
That's great.
Cool. All right. So hi all, this is Xiaofan from Shanghai, and it's pretty late night here. Thanks for Rayan to give us an impressive talk about Milvus use cases. Today I want to share with you guys about the details what is Milvus and how we build a vector similarity search engine. Okay, feel free to give me comments, questions in the chat box. Okay. So before we start, let me simply introduce myself and the company. So our company is Zilliz. I made this word from the English word zillion. So zillion is a very large number. So zillion of zillion, that describes the volume and wide use cases for the unstructured data. So it's also palindrome, so I think it's pretty good. So my name is Xiaofan, and I have 7 years working experience focused on building database and storage systems. So after graduation from Cornell University, I worked for Oracle, one startup, and also Alibaba Cloud. So now I was working at Zilliz as the director of engineering, also in charge of the Milvus project. So today my talk will be divided into 5 parts. The first part is I'm going to discuss why we believe Milvus is the next generation infrastructure for search. Okay, so the second part will review the motivation of Milvus and its evolution history. Okay, so the third part will go through how to build a cloud native vector database. Okay, so the first part we're going to go through several key optimizations in the system. Okay. So last part, we'll preview the next step of Milvus community and the project. Okay. So before we introduce Milvus 2.0, let's first go through why we need a vector database and what a vector database can do. Okay. So in the past few years, the concept of big data was very popular. So big data multiply AI will be the trend in the industry. To sum up, data are changed both horizontally and vertically. So there will be like rich data types, and we have those text, images, videos, and audios. So they all like have different data expressions, and it looks pretty much different. Okay, so this is a very annoying problem for a searching system. Because the underlying system prefers things that are abstract and unified. Okay, so like the relational model or the text which Elasticsearch do for search. Okay, so if you have different expressions, this brings great trouble to handle the unstructured data. Okay, so another big challenge is the semantics. Okay, so information hidden behind unstructured data need to be explored. So unlike traditional database, which focus on term or pattern match. Okay, so unstructured data search focus on the deep semantics. Okay, so it is usually a similarity issue rather than an exact match. Okay, so the common way to represent semantics behind data is through embeddings. Okay, so which is generated from feature learning. Neural network now has a very strong computing power to support us. Okay, so it can man the semantic information hidden in the data. Okay, so even for the same data set, embeddings could be pretty much different based on what information you want to extracting. Okay. For example, if you have a video and you want to use it for object classification or the anomaly detection, there should be like use totally different models and generate different embeddings. Okay. So embeddings is a good abstract. So it's split unstructured data handling into two parts. So the first part is how to convert data from different expressions into embeddings. Okay. The second part is how we can analyze embeddings in a vector space. Okay. So Milvus is a system working on the second part. Okay. So we build a database to support embedding similarity search. It is also called embedding retrieval. Okay. So before the burst of Milvus, data engineers use libraries such as FAST or HNSW to support vector search. Okay, so there are certain challenges to applying these libraries into production. First of all, how you're going to do data sharding or load balancing if you have a great amount of data. Okay, so with the growing of unstructured data, user has to handle billions of embeddings, and thus it cannot be running on a single machine solution. Okay. Secondly, you have to handle data delayed update, and especially on the online applications. Okay, so the traditional vector library usually does not support CRUD or it's not efficient. Okay, so also durability and availability will be a big issue for using those libraries directly. User has to handle those complicated logics themselves. Okay. That's why we developed Milvus. The first question is, what is Milvus? Okay, so Milvus is first of all a database. The original intention of this project to solve how to maintain meta information, and it can support CRUD operations. Okay, so Milvus is also listed on the DB rank at the position of 285. Okay. So Milvus also solved the problem of approximate near neighbor problem. Okay, it helps us to build index on those vectors, and which can help accelerate the embedding retrieval. Okay, so Milvus is a distributed solution. It is highly scalable and robust. We built Milvus on top of Kubernetes, so it's kind of a cloud-native design. The goal of Milvus is to build a system like Tesla. You can run it really fast and stable. Okay. Last part, but foremost, Milvus is open source. So it's now probably the world's most popular vector database on GitHub. Okay, and we want to make it also the most advanced database. Okay. The second question will be, what is not a Milvus? Okay, so first of all, it's not a traditional relational database. Okay, we didn't support ACID. We don't support SQL. So it's pretty much only doing the vector retrieval things. Okay. So secondly, Milvus is not aimed to replace Elasticsearch or Solr. Okay. So the database, the data type and the operation is pretty much different. Okay. So ES works on term search or text data search, while Milvus mainly works on semantic search on the embedding data. Okay. So there are like many reasons we want to build Milvus 2.0. The first one is the very complex semantics. Okay, we meet a lot of users who want to combine the usage of Milvus and Elasticsearch, combine the usage of Milvus and MySQL. And we found that the old system is very difficult to combine both systems. Okay. The second reason is we hate the cost efficiency problem. We have this new CAP trade-offs. C means cost, A means accuracy, and P means performance. So usually you can't fulfill all the three requirements. So user has to choose two of the three. Okay. So the third issue is how we're going to iterate this system very fast. Okay. So Milvus 1.0 aims to solve specific problems, and it lacks careful design, so which makes further iteration really tough. Okay. thus we start the design of Milvus 2.0, a cloud native vector database. It is blazing fast, easy to scale, and user friendly. Okay. This is the current journey of Milvus project so far. The initial idea comes from 2018, and we open sourced all the code in 2019. Okay, so now we just graduate from Alpha AI Foundation in 2020, and Milvus 2.0 releases on 2021. Okay. Okay, so the third part we're gonna do talk about the designs inside Milvus 2.0. So we pretty much learned a lot from LSM trees, Lambda architectures, and many other cloud native designs. Okay, so in this part, I will show you the thinking paths of designing such a complex system. Okay, the first thing we insist is log is the soul of the distributed system. Okay, log is all you need to build a database. By restoring all the historical logs, we can replay log to any point and building the database state of that point. Okay, log can be served in a system as different forms, such as key value stores, such as on S3 or like in memory. Okay, thus we can serve different workloads. Log is the key of our design since it solves the problem for data silo. Okay, so we'll talk about how logs is heavily used everywhere in the system later. Okay, therefore the key problem is going to be how we store the logs. Okay, if you're familiar with MySQL, HBase, Aurora, or like Cockroach DBs, they all have like different solutions for durability. Okay, so for MySQL, they have the active standby solution, and usually users will store the bin logs onto the read disk. Okay, so for HBase, they have the HDF solution to help them to do the replications. For Cockroach DBs, they have this Raft Paxos protocols to do the log consensus. Okay, so for Milvus, we're choosing a very different way. We rely on the log PubSub system to store logs. So the advantages of we use a log PubSub system is it can decoupling all the logs and servers. So it ensures that Milvus itself is stateless, make failure recovery easier. Okay, the second reason is the log store ensures the data durability, make sure data is replicated. Okay, also the advantage of introduction of a PubSub system is making the system more extendable. Milvus can integrate with other systems such as Elasticsearch, Solar, Cockroach DB to fulfill all those requirements such as text search. We can integrate with GeoMesa and InfluxDB for time spatial data, okay, because all this system can be one of the log subscribers. Okay, introduce those Kafka and Pulsar into our system greatly reduce the system complexity. Okay, it can help us to focus on the main value Milvus provides to the users, which is vector search. Okay, so we try our best to utilize major solutions in the industry to solve the rest of the problems. Okay, so log-based solution looks really beautiful, but we're still facing a lot of challenges. First of all, you cannot merely really on the playback logs to query because it is too slow. And also the amount of data to be replayed back will be like pretty, it's too large. So we implement a log snapshot. There will be a background task to consume stream data and package it into a snapshot. Okay, so the log snapshot is also called sales segment in Milvus. After segment grows big, we sell it and present it on object storage such as S3 or MinIO. Okay, so we can build a vector index and the scalar index onto this sales segment to make query faster. Okay, so in the read path, it's pretty much similar to the typical MPP architecture. We read all the segments. We do the map. It's pretty much like map reduce. We reduce the top key result and returns to the user side. Okay. So the next challenge is going to be how we ordering and do data alignment. Okay. So for the LSM tree solution, there will be always a log sequence number, which when you read to the log, all mutations are ordered by the sequence number. Okay, so the sequence number also used to the multi-version concurrency control mechanisms. So for a distributed system, it's going to be more complex about the ordering issues. Okay, if you're familiar with Google Spanner, or they use the TrueTime API to enabling the application to generate monotonic increasing timestamps. Okay, so CockroachDB, they have this hybrid logical clock, which composes the physical part and the logical part to prevent clocks from drifting too far. Okay, they also run this NTP protocol to synchronize the logs. For Milvus, we don't have customized clock hardware, and the latency requirement of write is not tight. So we have a centralized TSO, which we call it the timestamp oracle into the system. So each write operation goes through the timestamp oracle and fetch a logical timestamp. Okay, so once you have the logical timestamp, you can reorder all your write in the log streams. Okay, so make sure every time you consume it's always in order of the timestamp. Okay. For example, if you saw the diagram above, the data comes in the order like 1426, which is the timestamp. Okay, 4 shows before the timestamp 2. Okay, that always happens on the distributed system because you have like concurrent ingestions. Okay. Thus, we have this time ticker. Once you see the time ticker, it gives you a guarantee that all data before number 5 shows up. Okay, then you can go back to the window, say, okay, all the data before number 5 could be consumed and saved by the users. Okay, so the first window will be 1, 2, and 4, and 6 is left to the next windows. Okay, so thanks to the window mechanism, it's pretty much similar to the Flink watermark. So each time tick could devise a different time window and rearrange the data to ensure the data is in order. Okay. So another problem for the search system will be near real time, because Elasticsearch also have and Solr also have the same problem. When you read the data, user cannot see it in time. Near real time seems to be a very good trade-off between accuracy and efficiency. Okay, but it also brings a lot of trouble because the segments are flushed periodically to ensure data visible. The frequency of the flush is very important. If it's too fast, then you have too many small files, which on the other side reduce the efficiency. Okay, so if you have too slow for frequency for flush, then the data written cannot be saved for a very long time, and the invisible delay is very large. Okay, the more fatal problem is that for the near real-time docs, it's not giving user a strong guarantee. In the past, we saw the situation that flash can not catch up and make data invisible for several days. Okay, so Milvus 2.0 introduced a complex consistency mechanism, which we call it tunable consistency. Okay, so we can support strong consistency as well as those session consistencies and consistent prefix consistencies. Okay, so in most scenarios, we recommend users to use consistent prefix or eventual consistencies. So it could be search faster. Okay, but we still support strong consistencies, which could be used on the task scenarios and some cases where user really cares about their data accuracy. Okay, we also have this bounded staleness, which we can guarantee that data will be seen in less than, let's say, 10 seconds or 1 minute. Okay, it will be a like good guarantee for the users. Okay, so the first adjustments is we will make it into a microservice style. it disaggregates computing intensive, memory intensive, and I/O intensive tasks. Okay. So microservice is trained for the cloud native design. It can help us expand and shrink the cluster independently, and it could better cope with different workload scenarios. And it also reduce the impact of failure, reduce the recovery time, and like many of the components, if it is done, it even don't affect the user workload. Okay. Once we have this monitoring distributed tracing system, microservice make us easier to do troubleshooting and debugging. Okay. We also split the control point, the data point. Okay. It gives Milvus the ability to deploy across cloud and across data centers. Okay. So therefore, the whole architecture of Milvus come to the big picture. We think that Milvus is a advanced design because it's in line with the concept of cloud native. It also help to achieve better elasticity and availability. Okay, so the whole system takes log system as a backbone. Computation and the storage are totally disaggregated, and we unified stream and batch ingestion, as well as we have and we also have a very good like time tick solutions which help us to do this tunable consistency. Okay, what Plenty do in the next step is to extend the functionalities by integrate Milvus with different plugins. For example, if you want to do text search, you can have one Elasticsearch as the log consumer right after this POSA. So what we can do is a federated query between Milvus and Elasticsearch. Okay, and also we can have a key value store after the log broker. So what you can do is to do some very fast point queries and probably do the primary key deduplication. So the key component of this design is query node. Okay, so in Milvus, query node helps to receive and respond all queries from user applications. Okay, so ingest data first ingested to the log broker, and query node consumes of data from log broker into the main memory. Okay, we call this growing segment. Growing segment is able to query, but not very efficient. So when the size of growing segment reaches a predefined threshold, we set it to immutable and flush it into a persistent storage as a sealed segment. Okay, so we perform periodically data compaction to merge small sealed segment into a large segment, which can improve the read efficiency. If you take a closer look into the segments, we can see that each data entry may contain one vector field and multiple attribute fields. Okay, attributes here refers to traditional structured data. Okay, so both vectors and attributes are stored in a columnar fashion, with data in the same field stored together. If segments reaches a predefined size, we will stop to merging all of them and build an index to facilitate efficient queries. Okay, we support multiple vector index types such as FAST, the graph-based index such as HNSW, and tree-based index such as Annoy. Okay. For data query result, they are directed to the query node. We implement all the search logic and the corresponding optimizations in this component. Okay, so most of the search algorithms are implemented in memory fashion. So Milvus is both computation intensive and also memory intensive. So in addition to those distributed architectures, we also do a lot of optimizations to accelerate queries. Okay, so the first one we do is called cache-aware optimization. So in Milvus, users can submit multiple search queries in a batch. So multiple CPU threads are used to handle a batch of queries in parallel. And so in a native implementation, we assign one query to each thread per time. Okay, so the thread need to calculate the similarity between query vectors and all the data vectors. There are two major drawbacks for the method. The first one is the lackage of memory access locality, which results in high cache misreads. Okay, so in this implementation, only query vectors have the access locality. For data vectors, each memory read corresponds to only one similarity calculation. This is not very friendly for CPU cache. Okay, so the second issue is the limited parallelism when the number of queries in the batch is very small. Okay, because design achieves parallelism only based on the query vector size. Okay, so in practice, we saw a lot of users, they submit only one query per time. Okay, so in this case, there will be no parallelism. Okay, so for our solution, both data vectors and query vectors are divided into blocks. We process one query block each time, and each thread is responsible for data vector block. Vectors in the data block are compared with all query vectors sequentially. So when one query block is processed, we move to the next query block. In this manner, there is access locality for data vectors. One memory read of the data vectors is using multiple sequence similarity calculations. And then when there is only one query vector in a batch, the search it still can be executed in parallel. So we evaluated the performance improvement against the naive implementation, and with two types of CPUs with different cache size. So the result is pretty much impressive. The cache-aware optimization can achieve a performance improvement up to 2.7 times and 1.5 times respectively. And the smaller the cache size, you will get more significant improvement. So the second issue we're going to solve is attribute filtering. Okay, recall the vector search problem is to find top key vectors, which is the most similar to the query vectors. Then in Milvus, each data entry have multiple attribute data fields in addition to the vectors. Okay, for attribute filtering queries, we give an additional constraint on the attributes. We want to find the most similar vectors for those entries that satisfies attribute constraints. Okay, for example, so if you want to do search t-shirts, okay, so you may want to search t-shirts similar to the image, but it also costs less than $100 in a shopping applications. Okay. Or another example is going to recommend music to the users, which has only the male users. Okay. In Milvus, we implemented several strategies to support attribute filtering queries. So what you can do is you can do the attribute filtering first, then you conduct a brute force scan on all those results. Okay. Another solution is you can do the index-based vector search first, then you do a post-processing on the results. Okay. We also implemented a partition data solution. So if you filter in based on the partition tag, you don't need to go through all the segments. Only the segments related to the partition are searched. Okay. Also, we implement these cost-based solutions. It has a lot of different stats, probably based on the data in the system. Okay, so they can pick one of the solutions from the above strategies. If you want to know more about what Milvus did for this optimization, you can learn from our papers. We just published it on the Sigma 2 2021. Okay, so the name of the paper will be the Milvus, a purpose-built vector data management system. Cool. So the Milvus 2.0 is just in its infant stage. and there will be still a lot of work to do in the future. Okay, so the first step is to make it correct. We currently introduce chaos tests to help us on catching those bugs. We'll still keep working on doing more automated tests, especially for the random test. Okay, so the second part is to make it easy. We'll support more data types such as string, geolocation types, and JSON data types. We're also working on multiple language SDKs. Go is ready just this week. Java is probably going to be ready by the end of August. C++ and RESTful API will be ready by the end of this year. Okay, we're also offering tools to migrate from FES, HSW, and Milvus 1.0 to 2.0. Okay, so the third part is going to make it fast. So Milvus 1.0 works well with GPU and accelerates indexing and embedding retrieval. Milvus 2.0 has no GPU version so far, but we're still working on that. Okay, we also work with GSI, GraphCore, and some other hardware manufacturers to do those hardware accelerations. Okay, we are also researching on a new vector index. Okay, Google Scan seems to be a good try. We're going to import Google Scan into our into Milvus by the end of this year. We're also working on our own ANN algorithms. Okay, so it can be works on disk, so we don't need too much memories to run billions of the vectors. Okay, we're also working on scalar index such as bitmap or inverted index. So it also can be optimized the performance for heavy search. Okay. Last but not the least, we're going to make the Milvus much faster and smarter. Okay, so there are many trade-offs and choice when you want to optimize Milvus. Okay, so if you need to consider about your workload, system configurations, index types, and all kind of hardwares. Okay, so we want to avoid not tuning by introduce auto-tuning and reduce the complexity. Okay, so we've already started to collect stats about data access frequencies, system load, and other different metrics. Okay, hopefully we're going to implement this auto-tuning by the end of next big release. All right, thank you guys for listening. If you're interested in Milvus project and if you want to know any details about Milvus implementation, feel free to ask questions. You can also visit our website and GitHub. So Milvus 2.0 RC2 has already been released. Feel free to grab it from Docker Hub and test it. Okay, any contribution to the community is warmly welcome. Thank you guys. Yeah, that's it.
Fantastic. Thank you, Xiaofan and Ryan. Thank you very much for your talk. So we're now going to have a chance for questions. So if you have a question for either of our presenters today, please drop it into the Zoom chat and I'll ask it on your behalf. But we have quite a small crowd today, so let's see what we have. Does anyone have a question for our presenters on Milvus?
Dare I say it, I think we have a small enough crowd where you might just be able to unmute yourself and ask instead of trying to type your complicated vector search engine question into a Zoom chat box.
Why not? Why not? Good idea, Max. So yeah, if you've got a question, just unmute yourself and ask our presenters.
If there aren't any, I'll kick one off. Well, first of all, thank you. That was awesome. It's really good to see you guys looking at the durability problem as like a primary focus. My question was around, have you gone down the route yet of getting like a Jepsen test? I'm not sure if you're familiar with Jepsen, but it's like it's a tool set that will cause chaos in your distributed application and try to force it to drop data and break things. But it's a popular toolkit, and there's a consulting firm that does these tests to make sure that your claims really are your claims. I don't know if you've heard of that yet, but what I guess my question is, what tests have you done around the durability?
Cool, that's a great question. So we're doing some chaos tests, but I'm not sure about the Jefferson thing, but we're using a structure called chaos mesh. Okay, so it's also open source solution to do chaos on the Kubernetes. Okay, so we also implement a bunch of our like test cases such as kill the POSA, kill all those object storage, and running ingestion all those network and IO arrows. Okay, so it just start because Milvus like we run this chaos test like 2 or 3 months, help us to find like 20, 30 issues, but we'll keep running at that. Like we want to have this also our own chaos test to be open source, so it could help the other guys test such a complex distributed systems. Okay.
Cool.
Thank you. So do we have any other questions from the crowd? I can see
Okay, so it's
I'm sure there's some people here who could ask them questions.
I guess I might ask one question, Dmitry, here. I'm actually sorry I missed the beginning of your presentation. So maybe that question was already answered, but do you guys support like some kind of like atomic updates? Or like, you know, with vector databases, it's one of the problems is that sometimes you need to reindex everything in order to update. So, so how do you solve this problem in Milvus?
Okay, so by saying like atomic updates, you're saying ingestion or like similar behavior like backload?
I guess I mean like ingestion, like pretty simple kind of like viewpoint here that like some of the, like if you pick like graph-based algorithm, for instance, for vector search, like you need to reindex everything, right? If you have an update in your data, you need to reindex everything. So how do you solve this in Milvus?
Okay, so we split all the data from a collection into multiple segments. So each segment is immutable. So make it pretty much like easier to do reindex everything. So if you have like 1 billion of the vectors, you can split it into like 500 segments. Then you can you can just issue a rebuild index task to the index node, and it once it finish, it will notify the query node to load all the index into the memory. Okay. So that is it's all automatics, and we also support build multiple index on one data. So if you want to test like which index works better for your scenario, you can have like 3 different kind of index such as HSW and IVF flight, and you can like switch the index in one command.
Oh, that's great. Thank you. That's awesome.
Yes, it's clear to me you've built a pretty comprehensive system here. So yes, it's impressive to see the scale of what you're building. Maybe I can ask another question. So what are your plans to build up your community around Milvus?
Yeah, sure. So I think right now our focus is we're really trying to build up more of the open source community. Like we see all these very successful projects that you know, have a lot of great contributors and a lot of great users, and that's something that we're really trying to aim for right now. We're not really trying to get we're not focusing too much on getting like only like customers who will eventually pay for something. Our focus is really on just building up the general user base and building up the open source community.
Understood. Great, thank you. So do we have any other questions from the crowd? Last chance.
If there aren't any, I'll ask another one.
Sure, go for it, Max.
So I'm looking at you're supporting different quantization techniques, and for product quantization, you typically have to train specific to, if I understand things correctly, you have to train to get a code book for the vector space that you're working with. How do you handle that? Does Milvus do the training, or do you have to train outside with the loss function to get the code books for the feature vectors, or do you have to, or does Milvus handle that for you?
Okay, so we split the task into two parts. The first one is a model part. So you're gonna do train it yourself, and you got those embeddings and you ingestion into Milvus. So Milvus itself won't help you on the embedding part. Okay, but we're going to have some customized modules. So it's probably going to help us to implement some pre-trained model like before your data pipeline. So let's say if you have this pre-trained BART module and you want to deploy on Milvus, it is probably possible on next maybe 2 or 3 releases. But I don't have a plan to do this right now.
Okay, cool. I know you can't do everything all at once, but it's good to hear all these interesting things you're trying. Thank you. I know other people have questions. I'm going to call on somebody.
Well, we'll give it another couple of minutes. Who else has got a question?
Hi.
Well, I guess.
Sorry.
Go ahead.
Sorry. I'm Vincent from Paris, France. I had a question because I'm very new to vector search, and I'm old to full text search. And I've heard about Vespa doing vector search on the same meetup. So how would you compare with Vespa, and is it a pertinent comparison between Milvus and Vespa, or are you in totally different field?
Rin, did you hear the question? I didn't hear it clearly.
Sorry,
So,
I was asking about Vespa, the search engine, which has also a kind of native vector search. Vespa.
Yeah, I'm afraid that I'm not too familiar with Vespa's offerings, unfortunately. Xiaofan, are you familiar with Vespa at all?
Nope. I know a few like systems doing the exactly the same thing as Milvus do. There is one called Vivid, another one probably in the UI is called Pinecone, but I never heard about the Whisper stuff. Did you have the link? So maybe I can take a look later.
Yeah, I can post it in chat.
Okay. Did you mention which language have you used to code Milvus?
Okay, I would just type.
Sorry, can you repeat the question?
Which language, which programming language did you use for Milvus?
Yes. He's asking what programming language we used for Milvus.
Okay.
Because,
so Milvus is mainly implemented in Go. So the Golang is used for the distributed part. So the core part is used for C++. Okay. And we also have different kind of SDKs. Like we have currently we have Python, we have Node.js. We're going to have Golang, and next step we're going to have Java and C++ for the SDK.
But the core is Golang.
Yeah, so the core part is C++ because we want to make it fast, and the distributed system part will be like it's used in Golang.
Okay. Thank you.
Okay, so I think we'll bring things to a close now. Thank you both, our presenters again. Let me just.
Thank you all for coming and being here. Happy to present.
Yeah, it's been great. Let me just share my screen for our. Here we go. So just a couple of things to round off the event. Hopefully you can all see that. We're looking for more speakers for Haystack Live. So if you know someone who could give a great talk on search and relevance, or you can give a talk yourself, please get in touch. If you look at the haystackconf.com website, on the right-hand side, there's a call for papers. And yes, we're coming back with our own Haystack conference. We're hoping to do this the 29th and 30th of September. The call for papers for that is also open. And you look on the same website, it's on the left-hand side. That'll be 2 days of talks all about search and relevance in Charlottesville, Virginia. And we'll also have some social events, networking. More information and tickets will be on sale very soon. So we'll bring this to a close. Again, check out the video on YouTube. Do check out the Haystack website. And if you're interested in our training, do take a look at those. But thank you both our presenters and the team at Zilliz and talking about Milvus. And we'll see you all again at our next Haystack Live. Thank you very much. Goodbye.
Thank you all.
Thank you.
Have a nice day.
You too.